minus theta squared over 2 factorial plus theta to the fourth over 4 factorial and so on, right? You know? Well, just take it as a fact, right? It's okay, you can look it up. It's R1 times 1 minus, again, cosine will be 1 minus theta 1 over 2, theta 1 squared over 2, like so. Okay? And that means this, delta 1 is equal to approximately 1 minus 1 is 0, minus minus is plus, so it will be 1/2 R1 theta 1 squared. Okay. Nate, it's all together? Okay. And I should have used little r because it's the distance, but since little r1 is equal to capital R1, I would just say that. For delta 2, a similar reasoning, delta 2 will be 1/2 little r2 theta 2 squared, but little r2 is negative capital R2. Minus 1/2 2 theta 2 squared. Okay. And I need about 10 more minutes on this one. Let's see if we can one. So I have, let me see here. Yeah. So that's that. Let me put here delta 1 is equal to 1/2 R1 theta 1 squared. Okay. 1/2 theta 1 squared, which is equal to 1/2 R1. But since theta 1 is a small angle, then theta 1 is almost the sine of theta 1 squared. Okay. Theta 1 is a small angle, sine of theta 1 is almost equal to theta 1. Now what is the sine of theta 1? Well, this should say theta 2. The sine is the z over R1. Yeah, z over R1. Good. So it will be 1/2 of R1 times z over R1 squared, and that's equal to 1/2 of z over R1, z squared over R1. Does that make sense? Okay. Well, guess what? Delta 2 will be minus 1/2 z squared over R2, right? There is that extra minus sign for delta 2, all right? Okay. Now, the time that it takes to travel through delta 1 and delta 2 is not just the normal time. I have to multiply by a factor of n, because the index of refraction is not 1, it's more than 1, and so light will travel slower, so the time it takes will be proportional to n times the distance. Okay. So then the time of travel for L2. Let's look at L2. L2, it will be this distance, right? And then delta 1 plus delta 2, and then this distance. Yes? What is this distance? That's s minus delta 1. Yeah? S minus delta 1. And this one is s prime minus delta 2. And then plus the middle here that we have to multiply by n. So s minus delta 1 plus s prime minus delta 2 plus delta 1 plus delta 2. That distance, but that distance needs to be inflated by a factor of n, because there is an index of refraction. So I get here L2 is s plus s prime plus minus delta 1 minus delta 2, that's minus delta 1 plus delta 2 factored like so, plus n times delta 1 plus delta 2.
So 2 minus 2.
If we factor, so let's say we get L2 will equal to s plus s prime plus n minus 1 times delta 1 plus delta 2, okay? Delta 1 plus delta 2. And delta 1 plus delta 2 is this. So we get L2 will equal to s plus s prime plus n minus 1 times delta 1 plus delta 2. You'll have a factor of 1/2 z squared. And then 1 over r1 minus 1 over r2. And then 1/2 of z squared. Okay? That's L2. But I want L2 to equal to L1 because they took the same time. So if L2 is equal to L1, let's write down L1. It's there. L1, no, yeah, L1, which is s plus s prime. And then z squared over 2s plus z squared over 2s prime. You allow me 1 minute, so cancel, 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 cancel. And then on here, I have z squared over 2 on both of them, so I can also cancel that. So I have z squared over 2, 1/2 of z squared, that cancels. So let's see what's left. You get 1 over s plus 1 over s prime is equal to n minus 1 times 1 over r1 minus 1 over r2. That's the Lensmaker's equation. Okay. Sorry I took extra minute. I will stop here. Maybe next time I might review it a little bit, but not much.